Hi guys, in this video we'll be covering forces in motion 2. These are the topics that we're going to go through. Resultant force, resolution of forces, forces in equilibrium, and elasticity. Before we start, if you're finding this video helpful, please do remember to hit the like button. It really does help me a lot. Thank you very much for doing that. Let's get started. In this video, I'll be using this set of notes. If you'd like to get these notes from me, please do check the description on how you can do that. First, let's define the main terms in this topic. Resultant force. Resultant force is simply the vector sum of forces acting on an object. A free body diagram is simply a diagram that shows all the forces acting on an object. Resolution of forces is the process of resolving forces into two perpendicular components. We'll look at it in more detail a bit later. Elasticity is the property of a material that enables it to return to its original shape and size after the deforming force is removed. And finally, Hooke's law states that the extension of a spring is directly proportional to the force applied on the spring, provided the elastic limit of the spring is not exceeded. Another concept we need to be familiar with is equilibrium of forces. An object is said to be in equilibrium of forces when there is no resultant force acting on it. Let's start by determining resultant forces. Calculate the resultant force acting on objects in various scenarios below. First, let's look at forces acting in the same direction, such as this. Both the forces are acting downwards, and so the vector sum, the resultant force, is simply, we call this F, will be 4 newtons plus 6 newtons. Since both are in the same direction, as vectors, you can just add them together. So this will be 10 newtons. What if the forces are in opposite directions instead? Then what we have to do is, since they are vectors, we are going to assign one direction as positive and the opposite direction as negative. So how you want to do this is up to you. So let's say I assign this as the positive direction, then this will be the negative direction. The resultant force in this case is the vector sum, which is F is equals to positive 6 newtons plus negative 4 newtons. So it ends up being 6 minus 4. We are taking the difference, and this is 2 newtons. Notice that our answer is actually positive 2 newtons, indicating that the direction of the resultant force is in the same direction as the 6 newton force. Let's look at the next situation. What if the forces are perpendicular to each other? In the two previous situations, the forces were aligned. In this case, they are perpendicular. They form a 90-degree angle between them. So what is the vector sum of forces in this case? Here we have to draw our triangle. So we follow the direction, 12 newtons to the right. And then when we are doing vector addition, you add the second vector at the end of the first vector. So we start from here and we go 5 newtons in the upward direction. This is 5 newtons. The sum of these two vectors will be from the beginning point to the ending point. So this is the sum of the two vectors. Vector sum, which is the resultant force. This is the resultant force. How do we find the magnitude of this resultant force? Since they are perpendicular to each other, the two forces, we have a right angle triangle. And when we have a right angle triangle, F is the hypotenuse of this triangle, which means F is equals to the square root of 5 square and 12 square added together. And that would be 13 newtons. In this case, we are able to do calculations because we have a right angle triangle and we can use Pythagoras theorem. What if the forces are not perpendicular? They are acting in directions that are not perpendicular and they are not aligned as well. So in this case, we need to do drawing as well. But we cannot get a right angle triangle since the angle is not 90 degrees. And therefore, we need to use scale drawing. In scale drawing, there are two methods. The first is triangle of forces. In triangle of forces, we are going to do the same as we did earlier. So what we have to determine first is the scale. Since the magnitude of these two forces are small, that is 3 newtons and 5 newton, I'm going to set my scale to be, I'm going to set 1 centimeter to 1 newton. That is to say, every centimeter represents 1 newton of force. Now let's draw the triangle. In this case, we have 5 newton as the horizontal force, which means 5 newtons will be 5 centimeters. So I need to draw a horizontal line at 5 centimeters. Alright, now the next force is 3 newtons. This is a bit tricky because the angle here is 42 degrees. So you need to use a protractor and get an angle of 42 degrees from the horizontal, and then you need to draw 3 centimeters from this end. Remember, we are adding vectors here. So let's label this force first. This is 5 newtons. I'm going to add 3 newtons from here. So again, 3 newtons using our scale would be 3 centimeters. And so I'm going to draw 3 centimeters. And now we are going to find the vector sum. Again, what is the vector sum? When you add these two vectors together, you have the sum will be from the beginning till the end. Alright, I've already joined the line here, and this will be the resultant force. How do we determine the magnitude of this? We have to measure it. So use your ruler, measure the length of this. For me, this is 7.5 centimeters. And since according to our scale that we set earlier, 1 centimeter is to 1 newton, 7.5 centimeters will be 7.5 newtons. And so the resultant force here is 7.5 newtons. We can also determine the direction of this resultant force. That is, use the protractor and measure this angle. So this angle, after I've measured it, is about, let's say theta is equals to 15.5 degrees. The second method is the parallelogram of forces method. Now in this method, again, we are going to use scale drawing. So I'm not going to do an exact version here. I'm just going to very quickly summarize it. In the parallelogram of forces method, we draw the first force, 5 newtons, according to scale. So you need to measure 5 centimeters and draw. Next, you draw the second force from the beginning instead of the end. So it will be something like this. Once again, you need to measure the angle accurately, 42 degrees. Measure the length accurately, 3 centimeters. Draw the line. Now the parallelogram of forces, you use your compass. Use the compass and mark the first arc. This length would also be 5 centimeters. Remember, we are drawing a parallelogram, so you need to correspond to this length. And then you put the compass here, and then you measure this out to be 3 centimeters now. Remember, we are drawing a parallelogram. So you also draw another arc here, and so where they meet, that will be where you need to join your line. Okay, so this is just a rough model. So they're supposed to meet here. So our resultant force will be from the start to the end again. So you can see it's very similar to the triangle, but this time we are using parallelogram instead. And the method is the same. Measure the length of this resultant force. It will be 7.5 centimeters. Then using the scale, it is 7.5 newtons. And again, measure the angle to the horizontal, and you have the direction of the force as well. Let's go to B. Resultant forces on an object in various states of motion. Label all the forces acting on the stationary rectangular boxes below. Let's look at the first example. This object is on a horizontal surface, and all objects that have mass will definitely have weight. When we label weight, we should label from the center of mass. For an object with an evenly distributed mass, the center of mass will be the center of the object. And that is why we draw the arrow from the center for weight. And then, since the weight is acting on the table, according to Newton's third law, there will be an equal and opposite reaction acting on the box. And this is the normal reaction, R. So the normal reaction comes from the surface where the initial force is being applied, where the pressing force is being applied. For an object on the slope, if it is on a slope, once again, as long as the object has mass, it definitely has weight. Weight acts towards the center of gravity of the earth, which for us relatively is down. And then since the box is again pressing on the surface, Newton's third law, we have a normal reaction. We call it the normal reaction because the angle is 90 degrees to the surface on which it is acting. The box in this position has a tendency to slide down the slope. Therefore, there will be a force that is opposing this motion, and that is friction. Friction always acts against the motion, and so friction in this case would be up the slope. We're going to do F subscript R for friction. Let's go to number 2. Label all the forces acting on the objects in motion below. Now we have objects that are moving. Let's look at A. This car is moving down the slope. If the car is moving down the slope, then as usual, any object with mass will have weight, and if it's pressing on any surface against any surface, then there will be a normal reaction. Since it is going down the slope, there will be resistive forces acting up the slope. And of course, if the car, assuming that the car engine is still running and driving the car, so we have another force called the thrust which is the force exerted by the engine in order to move the car forward. Let's look at another example. Let's look at an airplane flying in the air. For the airplane, since it is moving this way, again we have resistive forces acting in the opposite direction, which is called the drag, which is just air resistance. And then we have, of course, the engine thrust working in the forward direction, and the plane definitely has mass, therefore it has weight, and there must be a force that is lifting the plane up, which is called the lift. Let's move on. Fill in the blanks. Newton's second law is commonly expressed as second law of motion. F is equals to ma. State whether the resultant force F, velocity v, and acceleration a is equals to or not equals to 0 for the objects in the following states of motion. First situation is the object is stationary. When the object is stationary, the velocity is 0. And the acceleration is definitely 0 since it's not moving in the first place. Now when the acceleration is 0, this means the resultant force is 0 because F is equals to ma. If a is 0, then the resultant force is 0. Object is moving with uniform velocity. So here velocity is not equals to 0, but acceleration is 0. Acceleration is 0 because there is uniform velocity. There is no change in velocity. And when acceleration is 0, then resultant force is 0. So it's important to note here that even while an object is moving, the resultant force can still be 0. Third situation, moving with uniform acceleration. In this case, velocity is not 0, the object is moving. Acceleration is also not equals to 0 because there is uniform acceleration. Therefore, the resultant force is not equals to 0. Let's look at number 3. State whether the resultant force is equal to 0 or not equal to 0 in the following situations. Let's look at B. A car moving with increasing speed. If it is moving with increasing speed, then acceleration is not equal to 0. Therefore, the resultant force here is not equal to 0. Let's look at C. The car is slowing down. If it is slowing down, that means acceleration is not equal to 0. Acceleration is actually negative. Deceleration is occurring. Therefore, resultant force is not equals to 0 as well. Let's go on. Solving problems involving resultant force, mass and acceleration of an object. In these examples, we are going to use gravitational acceleration is 9.81 meter per second square. Let's look at number 1. Jeevan dropped a pencil case of mass 200 grams. The pencil case fell to the ground with an acceleration of 7.8 meter per second square. Calculate the resultant force acting on the pencil case. Whenever forces and motion is involved, I always advise my students to draw the free body diagram first. You can always represent the object as just a circle. Let's label all the forces acting on the object. First, of course, we have the weight. And then, since the object is falling down, then there is air resistance as well in the opposite direction. And those are the only two forces acting on the object. Next, it's important to label the direction of acceleration. The object is accelerating at 7.8 meter per second downwards. So we have a downward acceleration. A is equals to 7.8 meter per second. The direction of the resultant force will be the same direction as its acceleration. And so we know that the resultant force is actually acting downwards. In this particular question, you will notice that we have a situation where we have forces in two opposite directions. And how do we find the resultant force of forces in two opposite directions? We choose one to be positive. The positive direction, we normally follow the direction of the resultant force. And so we take down as positive, up as negative. And now we are ready to write our formula for resultant force. Resultant force F will be equals to vector sum of forces here, that is W plus R. But R is in the negative direction. Therefore, negative R. And so this just becomes W minus R. Now that we understand the situation, let's try answering the question. Here they want you to find the resultant force. Now in this case, we already have the mass of the pencil case and we already have the acceleration of the pencil case. And so we only need to apply the fact that the resultant force is equals to mass times acceleration, ma. And when we are doing this, we should remember to use SI units. So the mass will be 200 grams is 0.2 kilograms multiplied with the acceleration. The acceleration is already in meter per second square. So multiplied by 7.8 meter per second square. And the answer is 1.56 newtons. This is the resultant force acting on the pencil case. Let's try the second question. Calculate the magnitude of air resistance acting on the pencil case. Based on what we did earlier, we already know resultant force is equals to W minus R. And now we know that the resultant force has a magnitude of 1.56 Newton. Therefore, all we have to do is W minus R is equals to 1.56. Don't forget that W is equals to mg, and so 0.2 times 9.81 mg minus R equals to 1.56. That would mean R is simply equals to 0.2 times 9.81 minus 1.56, and the answer is 0.402 newtons. Number 2 is a similar question as well. Again, if you'd like to get your hands on these notes, do check the description on how you can get them. Lee Kyung uses a lift as shown in the diagram on the right. So we can see the diagram here. Given that his mass is 63 kg, calculate the reading of the weighing scale. The reading that we see on a weighing scale is not actually a measure of the weight of the person. It is in fact a reading of the normal reaction, not the weight. In a situation where a person is standing stationary on the weighing scale, the normal reaction is equals to the weight, and therefore we can say that the reading on the scale is reflective of the weight. However, it is not actually measuring the weight. Let's try the question here. Let's say the lift is moving up with a constant velocity of 9.0 meter per second. Immediately when we see constant velocity, it must click that acceleration is equals to 0, and since acceleration is equals to 0, resultant force is equals to 0 as well. So forces are in equilibrium. Again, let's try a free body diagram. So just draw a circle, and then you have the weight acting downwards and the normal reaction acting upwards. These are the forces acting on Lee Kyung. Since we know that the resultant force is equals to 0, forces are in equilibrium, the sum of forces in any two opposite directions are equal. Therefore, we can say that R is equals to W is equals to mg, and this will be 63 times 9.81 mg, which is equals to 618.03 newtons. Let's try another one. Let's try C. Let's say it is moving downwards with an acceleration of 3.4 meter per second square. Again, we have the weight and the normal reaction. This time there is an acceleration. Acceleration is in the downward direction and the magnitude is 3.4 meter per second square. So already we know the resultant force is acting downwards. So we are going to take downwards as the positive direction, upward as the negative direction, just to make things easy. Now we can construct our equation. The resultant force is equals to MA, and the resultant force in the situation where we have two opposite directions, that is W plus negative R equals to MA. Therefore, W minus R equals to MA, and R will simply be equals to W minus MA. And so this will be equals to mg minus MA, which is 63 times 9.81. You could factorize the 63 minus 63 times 3.4. And the answer here is 403.83 newtons. Let's look at a question with the spring balance in a lift. An object of mass 15 kg is hung on a spring balance with a string. Spring balance is attached to the top of the lift as shown in the diagram. You can see in the diagram. Calculate the reading of the spring balance. Now once again, just like the reading of the weighing scale, the reading of the spring balance is not weight. The reading of the spring balance is actually the tension force that is exerted on the springs in the spring balance. And so when we look at this object, any object that is matter will definitely have weight. And then up here we have the tension force. This is the force that is reflected on the reading of the spring balance. Let's try a question. Let's try this. What if the lift is moving upwards with an acceleration of 8.3 meter per second square? Let's draw a free body diagram. Draw a circle, and draw weight and tension. These are the two forces acting on the object. The object is moving upwards with an acceleration. So acceleration is in the upward direction A is equals to 8.3 meter per second square. And now we also know that resultant force is upwards because acceleration is upwards. And so in this case, we take the upwards direction as positive and the downwards direction as negative, two opposing forces. So we can write our equation as F is equals to MA, resultant force is equals to MA, and the resultant force is positive tension plus negative weight equals to MA. So T minus W equals to MA. The reading on the scale is T, so T is equals to W plus MA. We just add W on both sides, and this will be mg plus MA, which is equals to 15 times 9.81 plus 15 times 8.3, and the total is 271.65 newtons. Next, let's look at objects with pulley systems like this. A trolley of mass 0.65 kg is pulled by a load on a smooth table. Smooth table means there is no friction or negligible friction through a pulley as shown in the diagram on the right. Given that the trolley moves with an acceleration of 3.9 meter per second square. Let's take a closer look at the objects here. The trolley is pulled by the string, and so the string is pulling the trolley this way. There's a tension in the string, and there's a tension pulling the load upwards as well. So this is tension as well. These two values of tension are the same because there is only one string. There is a single string. If there is one string, then there is only one tension force within the string when it's taut. Let's look at the other forces here. Trolley has mass, therefore there is weight, and since it is pressing on the table, we also have a normal reaction. And then we have the load. The load has mass as well, therefore the load there will be weight. So to differentiate this, I'm going to put weight of trolley, WT, and weight of load, WL. So these are all the forces acting on these two objects. The question also gives us the fact that the trolley is accelerating at 3.9 meter per second square. And so there's only one direction for trolley to move, and that's this way. The acceleration is 3.9 meter per second square. What about the movement of the load? Since they are both connected by a string, the movement of the load must of course be identical to the movement of the trolley, and therefore the load is also accelerating at 3.9 meter per second square. But of course the direction of acceleration for the load is downwards. Let's try a question. The tension, calculate the tension in the string. When we look at this diagram, we look at the motion of the trolley. The resultant force acting on the trolley has to be towards the right. This is because the acceleration is towards the right, and therefore we are going to look at all the forces in this direction. So the sum of forces, the vector sum of forces on the trolley in the right direction, we only have a single force acting on the right, that is tension. So the tension force is in fact the resultant force. There is no force acting on the left, not even a component force. And so we can write T is equals to MA. Mass of the trolley was given 0.65, acceleration is 3.9 meter per second, and the answer is 2.54 Newton. Let's look at another type of pulley system question, this one, where you have two masses hung like this. The two loads A and B of masses MA and MB respectively are connected by a string that passes over a pulley as shown in the diagram on the right. Calculate the tension in the string and the acceleration of the load when the first one, mass of A is 3.5 kg, mass of B is 3 kg. Let's look at all the forces acting on these two objects. We have the string pulling the objects upwards, so we have tension force, and then since they have mass, they definitely have weight. And so these are the only two forces acting on both objects. Let's draw the free body diagram. We have A and B, and then we have the tension force acting upwards. Remember that they are both connected by the same string, therefore the tension will be the same. And then we have weight, let's call this WA and WB. Now we've got to figure out the direction of acceleration. The first mass A is 3.5 kg and B is 3 kg. And so we know that A is going to be moving downwards simply because it is heavier. So we will have an acceleration downwards for A, And B, because it's connected by the same string, is forced to move upwards because it is lighter. But both will be moving at the exact same acceleration. Their motion will be the same because they're connected by a taut string, except for the direction. From this, we can form two different equations. Let's look at A first. For object A, we have the acceleration downwards, which means the resultant force is downwards as well. And so we take downwards as the positive direction, upwards as the negative direction. And so the resultant force, which is equals to MA, is downwards direction W, positive W plus negative T is equals to MA. Let's fill this in. We are talking about A, so WA and MA. For B, the force is upwards, resultant force is upwards. So once again, F is equals to MA. And it is T that is in the positive direction this time because T is upwards and then W is downwards. So again, positive T plus negative W equals to MA. This is of course for B. You can see from this that what we have is actually simultaneous equation. Let's go on to solve this. WA will be 3.5 times 9.81 minus T equals to 3.5A. Here is mg as we've been doing earlier. And then this one, it will be T minus 3.0 times 9.81 equals to 3.08. Now we have our two equations, 1 and 2. We have two equations, two unknown, we solve by simultaneous equation. Since we have negative t and positive t, all we have to do is addition of the two equations. So I'm going to do 1 plus 2. We will get 3.5 times 9.81. T is already eliminated, so we go with this minus 3.0 times 9.81 equals to 3.5a plus 3.0a. Put this in your calculator and you get 4.905 is equals to 6.58. Therefore, a is equals to 4.905 over 6.5, which is 0.75 meter per second squared. Now we can substitute this value into either equation 1 or equation 2 to find the value of tension. I'm going to choose 2 simply because t is positive here. And therefore, when a is 0.75, t minus 3.0 times 9.81 equals to 3.0 A, which is 0.75. So therefore, T will be 3.0 times 0.75 plus 3.0 times 9.81. And the answer here is 31.68 newtons. Let's go on to the next topic. Resolving forces into two components. Remember from our definition earlier, resolution of forces is resolving forces into two perpendicular components. The forces that are components of the original force must be 90 degrees with each other. Let's try 8a. Resolve the following forces into horizontal and vertical components. The force here is 81 newtons. You can see the angle with the horizontal is 48 degrees. So we will have one horizontal component, I'm going to call Fx, and then we will have another vertical component downwards, Fy. Once again, we must remember that forces are vectors, and so when you draw the component of this force, it cannot be greater than this length because it is a component of this force. This one as well, for the vertical component we must remember is a component of this force, and so it cannot be greater than this. It will be exactly up to here. And therefore, if we combine these three forces together, we actually have a right angle triangle. So the vector sum of the vertical and horizontal component, or whatever components you choose to resolve to, the vector sum must be the force itself. And so let's try to draw our triangles as we did earlier. Let's start with Fx. It doesn't matter what you start with. Let's start with Fx, and then we add on Fy. So Fy is vertically downwards, and so we are going to start at the end of the first force. We are adding them together, Fy. The vector sum of these forces is the original force itself. So this is 81 newtons. And remember, the vertical and the horizontal components are perpendicular to each other. And therefore now we have a right angle triangle. We also have one angle, that is the angle between the horizontal component and the force. And so this is the angle between the horizontal component and the force, and this angle is 48 degrees. Now we have a right angle triangle. We can use either Pythagoras theorem or we can use our trigonometry, sine, cos and tangent of an angle. Since we already have the hypotenuse and the horizontal component is adjacent to the angle, then we can use adjacent over hypotenuse, which is cosine of the angle. And therefore, cosine of 48 degrees is equals to f of x, which is the adjacent side to the angle, over the hypotenuse, which is 81. Therefore, fx is equals to 81 cosine 48 degrees. This value is 54.20 newtons. Let's look at the vertical component. The vertical component is opposite to the angle. And so, once again, we have the opposite side and we have the hypotenuse. So, we are going to use opposite over hypotenuse, which is the sine of the angle. So, sine of 48 degrees is Fy over 81, which means Fy, the vertical component, is equals to 81 sine of 48 degrees, which is equals to 60.19 newtons. Let's say we wanted to resolve a force not in the horizontal and vertical direction. Resolve the weight of the object into a component parallel to the slope and perpendicular to the slope. Let's draw the force here. The force weight is downwards. We want components parallel to the slope. So the component force that is parallel to the slope will be in this direction up to here. Let's call this Fx, and then perpendicular to the slope, so it will be up to here. Let's call this Fy. Now immediately you should mark the angle whenever there's slopes. This angle, whatever it may be, will be the same as this angle. That's because when we work it out, this is a right angle triangle. This angle is 21. That would mean this angle is 90 minus theta. And this is another right angle here, which means this angle will be 90 minus theta, which is just theta. And so whatever angle is here will be the same here as well, 21 degrees. If you look at this diagram carefully, you actually already have your two triangle of forces. This is also Fy, the same magnitude and same direction, and this is also Fx. Now we can either use this triangle. Let's try this triangle. Let's draw this out again. Fx, and then we add Fy. You must get the downward force of weight as the vector sum. The angle is between the Fy and W. So the angle between Fy and W is here. So this is 21 degrees. And the 90 degrees is always between the two component forces. They are perpendicular to each other. So once again, we have ourselves a right angle triangle where W is the hypotenuse. This is the angle. So this is the side that is opposite to the angle, and this is the side that is adjacent to the angle. And so if we wanted to find Fx, we are going to use opposite over hypotenuse, which is sine. So sine of 21 degrees is equals to Fx over W. Fx is equals to W sine 21 degrees. The mass of the object here is 3 kg. So this will be mg 3.0 times 9.81 times sine of 21 degrees. And the value here is 10.55 newtons. Let's look at Fy. Fy is the adjacent side. And so we are going to use adjacent over hypotenuse, which is cos. So cosine of 21 degrees is equals to Fy over W, and Fy will simply equals to W cos 21 degrees. And that is 3.0 times 9.81 times cosine of 21 degrees. And the answer is 27.48 newtons. So far we've been drawing triangle of forces for forces where there are resultant forces. Here we are going to look at how to draw triangle of forces for forces that are in equilibrium. Once again, an object is in equilibrium when the resultant force F is equals to 0. There's no resultant force. Let's draw the triangle of forces for the forces acting on the box resting on the slope. First, let's identify the forces. As long as it has mass, it has weight, it is pressing on the slope, therefore we have a normal reaction to it, and it is tending to slide downwards, which means we will have frictional force in the opposite direction. Now we have three forces, and all these forces are in equilibrium because it is resting on the slope. There is no acceleration. When acceleration is equal to 0, that means resultant force is equal to 0 as well, as we know from earlier. So what is the vector sum of all these three forces? The vector sum of all these three forces will be 0. And how do we represent that in terms of vectors? A little bit of add maths here. If you remember, a 0 vector is simply a dot. It has no magnitude and therefore it has no length. And so when you sum up all the forces, when forces are in equilibrium, the vector sum is 0, and so the vector sum is just a dot. Let's see how that works out in our diagram. Let's start with weight. Okay, you can start with any force. I'm going to start with weight. Okay, weight is downwards, and then let's add normal reaction. So normal reaction is going to go this way, R, and then let's add the friction. So the friction is going to go this way. So as you can see, the vector sum of all forces is this dot, which is 0. And so when it comes to forces in equilibrium, you will notice that all the arrows are in the same direction. All are anti-clockwise. This is a sign that all forces are in equilibrium. If we compare to a triangle that we did earlier where there is a resultant force, for example, we know that this example, weight was the resultant force because weight is the vector sum of the two component forces. You can see that the direction of weight is opposite to the direction of the other forces. So these two forces are in the clockwise direction, whereas weight is in the counterclockwise direction. So these two forces are in the clockwise direction, whereas weight is in the counterclockwise direction. This is how you know that there is a resultant force. Let's look at solving problems involving forces in equilibrium. Find the thrust of the engine of a car traveling up a slope at a constant speed of 22 meters per second. If the mass of the car is 2,680 kilograms and the resistance to the motion is 10,370 newtons. The inclination of the slope is 17 degrees. Let's draw as usual. We have to draw a free body diagram. You don't actually have to draw a car. Just draw a circle to represent the car. The car has weight and then there is normal reaction and there is the thrust of the engine. It's going up the slope. So T, since it's going up, resistive forces are down the slope, Fr. And so let's label the forces that we know. Resistance to motion is this, so this will be 10,370 newtons. And then we have the weight, which is mg, and so this will be 2,680 times 9.81. And immediately you should draw a line that is perpendicular to the slope and label this angle. So from earlier we know that since this is 17 degrees, this is 17 degrees as well. Let's check the question again. We want to find the thrust of the engine, so we want to find T. When you want to find T, we look at all the forces in the direction of T and in the opposite direction. Now we have to determine whether there's a resultant force or not. When you look at the question, the car is traveling at a constant speed. Constant speed means acceleration equals to 0. And when acceleration is equal to 0, resultant force is equals to 0. Therefore, we know that forces are in equilibrium. There is no resultant force. That is to say, the sum of all the forces acting in the direction of T, up the slope, is equals to the sum of all the forces acting in the opposite direction, down the slope. The sum of all the forces in any two directions, any two opposite directions, must be equal. Only then can you get a resultant force of 0. Let's look at all the forces acting up the slope. We have tension. So we have tension here. Anything else? There is no other force acting up the slope. We have to check for components of forces as well. You only check up to 90 degrees from the force. So when we look at weight up to 90 degrees is only here. So weight has no component up the slope. Now let's look at all the forces acting down the slope. Normal reaction is 90 degrees to the slope. It's perpendicular to the slope. So it will not have any component. You can try to find the component of a force at 90 degrees. You will see why it is 0. The forces acting down the slope is the resistive force. So we can add it here, 10,370. And then now we have a component of weight, because weight has a component until here, which means weight has a component here. And this angle here will be 90 minus 17, which is 63 degrees. Now we have to add on the component of weight as well. So if we look at the component of weight here, this is adjacent to the angle. And so we are going to use adjacent over hypotenuse. Let's call the component Wx. So Wx over the hypotenuse must be the force itself. Weight is equals to cosine of 63, which means the component is W cosine 63 degrees. And so this is W cosine 63 degrees. There are other ways to do this and shorter ways to do this. You can check out my video for resolution of forces. I have a video specifically for that. I'll leave the link in the description below. So T is equals to 10,370 plus mg cosine of 63 degrees, and this will be 10,370 2680 times 9.81 times cosine of 63 degrees, and the sum is 18,056.69 newtons. Let's look at the next subtopic, the relationship between force and extension of a spring. For Hooke's law, the formula is F is equals to Kx, where K is the spring constant and X is the extension or the compression of the spring. Let's look at number 11. A spring with initial length of 11.2 centimeters extends to 12.2 centimeters when a load of 400 grams is hung from it. Calculate the length of the spring when a load of 600 grams is hung from it. From the formula F is equal to Kx, we know that F is directly proportional to X. That is, K is equals to F over X. F over X is always a constant. Therefore, we can use F1 over X1. One set of data must equals to F2 over X2, another set of data, because F over X is a constant. When we use this relationship, the unit that we substitute into this doesn't have to be the SI unit, as long as the unit on the left and the right is the same. And so I'm going to stick to grams. On the left side, let's write what we want to find. So we want the length of the spring when this load is hung from it, which means actually we want to find this. So the force will be 600 G. This G is not for grams, this G is for gravitational acceleration over x1, which is what we want to find. Let's look at the other one, 400 G. Then the extension when this is applied is 12.2 minus 11.2. That is the extension. So let's calculate that separately. 12.2 minus 11.2, which is 1.0. And so this is 1.0. So if you notice from this equation, we can eliminate G on both sides of the equation by division. And therefore, when you are using this method, you actually don't have to include G into the formula. You can just use the mass itself. Now we can solve. X1 will be equals to 600 over 400 times 1.0. And the answer is 1.5 centimeters. How do we know it's centimeters? Because you substituted 1.0 centimeter here. Left and right will be the same units. Now we are ready to answer the question. The length of the spring. The length of the spring when we hang 600 grams of load will be the original length plus the extension. And the original length, as stated in the question, is this 11.2 initial length, 11.2 plus the extension 1.5, and therefore the length of the spring now will be 12.7 centimeters. Let's look at the next part. Analysis of the graph of force against extension of the spring, F against X. The gradient of this graph will be the change in F, which is the Y value, over the change in X, which is the X value. And what is the change in Y over the change in X, change in F over the change in X? This is K. And so the gradient of this graph will be the spring constant K. The area under the graph will be, this is a triangle, and so we have area under the graph is equals to half times the base, which is the change in x, delta x, times height, which is the change in f, times the change in f. This is 1 over 2 delta f times delta x. 1 over 2 delta f is actually the average force times the displacement, and so you can see we have ourselves an equation for work done, which is energy. So this is the elastic potential energy. The area under the graph of a graph of f against x is elastic potential energy, E subscript P. Let's look at the factors affecting the value of the spring constant. The spring constant represents the amount of force required to produce 1 unit of extension. Let's take this slinky spring for example. So if the spring constant is small, that means I only require a small force to extend the spring this way. But if the spring constant is high, I require a large force to extend the spring to the same extension. And so we can look at the spring constant as how difficult it would be to extend the spring. The larger the value of spring constant, the more difficult it will be to extend the spring. What is the effect of the material of the spring? Different materials will produce different spring constants. Some materials will be stiffer than others. Length of spring. A shorter spring will have a higher spring constant. A shorter spring will be harder to pull than a longer spring. And so the longer spring has a lower spring constant. It's easier to pull. Next, the diameter of the spring. Diameter of the spring is this diameter. The diameter of the spring itself. Not the diameter of the wire that makes up the spring. It is this diameter. And so, if this is wider, it's going to be easy to pull the spring. Just like this slinky. It's very easy to pull it because the diameter is very wide. Whereas if we had a very small diameter, it would be harder to pull. And so, for a smaller spring diameter, we have a higher spring constant. And for a larger diameter, we have a lower spring constant. Now, what about the thickness of the spring wire itself? What about the thickness of this wire? The thicker it is, of course, it's going to be harder to pull. Thinner it is, the easier to pull. And therefore, a small diameter of wire will have a lower spring constant, whereas a large diameter of wire will have a higher spring constant. Let's move on. Solving problems involving force and extension. When we have a single spring and you apply the force here, F, then you get extension. Let's say the extension is X here. Now what happens when you arrange the springs like this? This is called arrangement in series. When you arrange the spring in series and you apply the force F here, so the force is the same, but now we have two springs. What is the force on the first spring? The force on the first spring will also be F. You can treat this as a single string. So the force that you apply will be distributed throughout the string. So the force acting on the first spring is F. The force acting on the second spring is F as well. It is distributed along the string. And so we know that when the spring experiences a force of F, the extension should be X. And so the extension here is X and the extension here is X as well. And what is the total extension then? Since the extension is vertical like this, we have an extension of X and X. The total extension will be 2X. We sum them up, we add them together. What about if they were arranged in parallel like this, side by side? When they are arranged in parallel, this force, again the force is F, but what is the force acting on each individual spring? Remember that they are identical springs. When the force is used to pull two springs in parallel, then the tension force here, by using forces in equilibrium, we know that two of the tension forces must equals to this force. And so the tension force is actually half the force, which means the force experienced by each spring is F over 2. And when the spring experiences a force of F over 2, since F is directly proportional to X, the extension will reduce by the same rate. So X over 2 as well. And now the total extension of this system, this is extending by X over 2, this is extending by X over 2 as well. But since they are side by side, they are not vertical, they are both arranged side by side, and so the total extension will only be X over 2. Let's try a question. Spring Q with original length 2 cm has a new length of 2.4 cm when a force of 0.2 newtons is applied to it. For the arrangement below, find, what we're looking at here is a combined arrangement. There's springs arranged in series and their spring arranged in parallel together at the same time. When you have an arrangement like this, you have to look at each level separately. You calculate each level separately. And so when you see this level, you would calculate it as if there was only a single spring involved. Let's find the force experienced by the spring. Let's look at the third level. The force experienced by this spring, it will take on the full force, which is 3.2 newtons. But when we look at the force experienced by E and F, these are two springs arranged in parallel. And since they are sharing the force, then the force experienced by E, since they are identical, they will be exactly the same. And the force experienced by F is the same, which is the force divided by the number of springs. In this case, we have 2. So 2, which is 1.6 newtons. Next, let's find the extension of each spring. Since J is experiencing a force of 3.2, using the formula F is equals to Kx, we know that the extension will be F over K. Now, the problem is we don't have K yet. How do we find K? From the original question, we know that there has been extension of 2.4 minus 2.0, which is 0.4 centimeters, when a force of 0.2 newtons is applied. Therefore, K will be equals to F over X. When the force is 0.2 newtons, the extension is 0.4. And therefore, K is 1 over 2. Now, we're going to maintain this as Newton per centimeter because our extensions here, we're going to calculate in centimeter. And so, the extension of J will be 3.2 newtons over 1 over 2 newtons per centimeter. And the answer is 6.4 centimeter. This is the extension of J. What about the extension of E and F? So the extension of E again will be equals to the extension of F, the identical springs, which is, you can use half the extension or you can just calculate again F over X, which is 1.6 newtons over 1 over 2, which is 3.2 centimeters. That's it for this video, guys. It's been a long one. If you've learned something, please help me hit the like button. Thank you very much for doing that. Do share this with all your friends if you think it is helpful and it has helped you understand this topic better. If you want to see more videos like this, do subscribe because I'll be producing at least one video a week. Don't forget to check the description if you want to know how you can get your hands on these notes and how you can support me as well. See you guys in the next one.